I'm going to talk about the diversity and body size evolution in parareptiles. This is part of my PhD that actually is a larger scale project that tries to disentangle the macroevolution of all early tetrapods, so trying to have a look at the first 200 million years of tetrapod evolution, but here we'll just focus on the parareptiles. Before I get to the actual topic, I would like to thank my supervisors, Mike Bent, Marcello Ruta, and Alex Stanhill. I would also like to thank the Paleontology research group for helpful discussions on R and model fitting, and I would like to thank NERD for funding this PhD. Yeah, so what are parareptiles? They are small extinct clades of early amniotes. They lived from the latest Carboniferous up to the late Triassic, were globally widespread, quite diverse in terms of ecology and morphology, also quite diverse in terms of body size. You have these small critters with a snout vent length of less than 15 centimeters, and also these large, bulky herbivores, the Pariasaurs, which were up to 3 meters long. So quite interesting group, I would say, but despite its properties, they have been largely neglected in recent macroevolutionary analysis. So I think this is even more of an incentive to have a closer look at this clade. So what you can see here is a phylogeny of parareptiles. It's part of an informal supertree of all early tetrapods. This phylogeny has been timescaled using the equal method as proposed by Rosati et al. In 2008. I've also tried to use the Carl-free method, and it seems to work for parareptiles. At least you get values that you could assume to be trustworthy. The problem is if you use the same method for the complete data set, then it doesn't work. So you have to estimate 3 rates for this method, the origination rate, the extinction rate, and the sampling rate. And for the complete data set, I get sampling rates over 100%, which is unlikely to be true. So I still have to figure out why that's the case. If someone has a suggestion, just feel free to comment on this. So what I've been doing so far was collecting data on the parareptiles, so expanding a pre-existing data set on early tetrapods, with including a stratigraphic range, proxies for body size, information on diet, and also an index that gives an indication of the completeness of the specimens known for the taxa in question. And at the same time, as I said, I've also compiled this supertree of early tetrapods. So what you can see here is a plot of the raw taxic richness of parareptiles throughout the Paleozoic and Mesozoic. And as you can see in the Paleozoic part, you have several peaks and troughs. You have a major peak in the Wardian. You also can see actually that the PT event didn't have a negative impact on the overall diversity of parareptiles, and indeed we have a second peak in diversity right afterwards. The diversity then decreases quite rapidly, this fades then out, and the clade was extinct at the end of the Triassic. Now we all know, of course, that the fossil record is incomplete, and the raw taxic richness doesn't necessarily reflect the actual diversity of the parareptiles. And different methods have been proposed to overcome this problem. I've been using a phylogenetic diversity estimate, and that's what you get here. So here we have the phylogenetic diversity estimate for parareptiles. The black curve is a median for several iterations done for the phylogenetic tree. So I had to randomly resolve polytomies within my Parareptilian subtree. And the gray shaded area is the 95% upper and lower quantile. So what you can see here is that throughout the Paleozoic, we no longer have these peaks and troughs, so it's more of a steady increase in diversity. Also, the Wardian peak is more or less gone, definitely not as prominent as it was before. What you also can see is that still the PT event did not have a negative impact on the overall diversity of parareptiles, and indeed, right afterwards, we have a massive increase in diversity. Otherwise, for the rest of the Mesozoic, actually, it looks pretty similar to what we have seen before. This already brings me to the body size analysis. So I've chosen femur length as a proxy for body size. There would be other possibilities, but I don't have the time to go into the details, so I just went with femur length. The problem is, however, that for parareptiles, there are just not enough taxa known with femora, so I had to cheat a little bit, use skull length to estimate additional femur lengths. I went with an ordinary least squares approach. I've also tried the phylogenetic generalized least squares approach. The problem with that is, if you want to estimate the lambda parameter, which gives you an indication of how much phylogenetic signal you have in your data, if you want to estimate that parameter as well, it doesn't work for all of the timescale trees. And if you have a look at the likelihood surface for the lambda parameter, you see it's quite flat, so it's probably again just due to a small sample size. So I went with the or less approach, as has been done before. Yeah, so I won't talk much in detail about the models of trait evolution. The overall idea is just so you have your data points, your body size, proxies, and they are not independent from each other. The taxa are related to each other through phylogeny. They have a shared evolutionary history, and this needs to be accounted for. And one way of doing this is by using these models. So one of them is the Brownian motion model. And in the Brownian motion model, the Brownian motion model is a stochastic continuous time random walk where changes in the trait values from one time to the next time are drawn from a distribution with a mean 0 and a variance sigma squared, and indeed if you increase the sigma parameter then the variance increases. So the important point is that the expected variance increases linearly through time, so you have sigma squared multiplied with t. The OU model, the Ornstein-Rudenbeck model, is just a modification of the VM model. The difference here is that you have a trait optimum, so the trait values are drawn towards this trait optimum, and the strength of attraction to this optimum is given by the parameter alpha. Otherwise, it's pretty similar, so again, the expected variance increases linearly through time. Yeah, this already brings us to the results. So if we have a look at the femur length, including the estimated femur length, we see that the OU model is favored. This is also true if we use other potential proxies for body size, like the mandible length or the skull length. There's one exception, so if we have a look at femur length without those estimated femur lengths, then the trend model is favored over the OU model. But I would blame this just on the small sample size. So overall, we could say, well, actually, the OU model is pretty well favored within the data set. There's one problem with that. There was an article by Cooper et al. 2016, and they have shown that for small paleontological data sets, the OU model is frequently incorrectly favored over competing models. And what they proposed was to use a Bayesian approach or simulations to overcome this problem. I've tried the Bayesian approach a little bit. Unfortunately, I haven't been able to finish those analyses because they are computationally much more demanding. So for now, I can just tell you it seems that the OU model is favored, but more needs to be done to be sure about this. If we have a look at different properties of the Parareptilia, like for example the diet, one could actually assume, well, so far we have just seen models that have a homogeneous evolutionary, or assume a homogeneous evolutionary rate, except for the early burst and the trend model. And when we see this distribution of the diet, for example, so it's changed from insectivorous Parareptiles to herbivores, one could say, well, maybe actually there's a change in the evolutionary rates, so we would expect to see heterogeneous rates, changes of rates across the branches. And indeed, if we have a look at the body size distribution, we have the large bulky pariasaurs here indicated in blue, and they're clearly different in terms of body size in respect to the other Parareptilian species. So just by having a look at this data, you would actually expect to see heterogeneous rates. So I've been using stable traits to model heterogeneous rates on the Parareptilian phylogeny, and indeed for the branch leading to the pariasaurs, you get an increase in the evolutionary rates of 4 times, and for another branch, for example, in the Procolophonids, you even get an increase of 10 times. Problem with that is that the homogeneous rate Brownian motion model actually is favored over the heterogeneous rate model. It's a little bit unexpected, a little bit difficult to explain. It could again be due to a small sample size, but I guess an alternative explanation is that we have seen for the homogeneous rate models that the OU model was favored, at least potentially favored. And here I've just been using the Brownian motion model, so the next step would be to model OU models with heterogeneous rate, also potentially with different trait optima, and then see whether I get the same result or whether we get the same thing. And that's it already. So the conclusions, as we have seen, the overall diversity of Parareptilia has not been negatively affected by the PT event. It seems that the OU model is favored over the competing models, but more analysis are needed to be sure about this. And it also seems that so far a homogeneous Brownian motion rate model is favored over a heterogeneous rate model, but more needs to be done to be sure about this. That's it.